So this is the final in a series of 3 talks about observation error correlations, which is just a snapshot of the work that we've been doing at the University of Reading. And so we've heard about the influence of correlated observation errors on the computational work required for variational systems, and how it's important to understand how they interact with the a priori correlations. But how do we actually diagnose these errors? I think there was a question maybe yesterday saying, well, how can we understand what these errors are? But we've also had one talk on how to use Bayesian estimation to get observation error correlations. But there are also other methodologies. So there's kind of an approach, like a bottom-up approach, where you say, well, we think these errors come from here, here, and here. You make some estimates and you add them up. And there's also these diagnostics from Gérald de Rosier, who was at Météo France, and that's what I'm going to focus on here. Okay. So we heard a bit of this motivation. Why do we care about observation error correlations? And it's partly because we are discarding a lot of data because we don't understand these statistics. And we have to calculate them statistically using some of the methodologies that I've just mentioned. But they will be dependent on your operational configuration. So the representation error that's been mentioned is going to depend very strongly on the resolution of your model. So we can't just do a one-off estimate for radar and use it everywhere. And we've heard that using these errors can lead to improvement. Okay. So these de Rosier diagnostics do exist to estimate observation error statistics. Now, the de Rosier diagnostics don't just exist to estimate observation error statistics, but there's also a set of 4 diagnostics that allow you to estimate background errors, analysis errors, or innovation error statistics. But originally, this set of 4 diagnostics was designed for use with best linear unbiased estimator schemes. And they've since been proven to also work with variational methods. But again, as we've seen at this symposium, ensemble methods are becoming increasingly important and definitely popular in NWP. So the aim of this talk is to see if we can apply these diagnostics that have been used in variational schemes to ensemble schemes. But before I tell you about the diagnostic in an ensemble scheme, I'll just tell you a bit about the standard diagnostics and why they've become so popular, really. So these diagnostics make use of very simple bits of information: your background residual or innovation, and your analysis residual. So these are pieces of information that, once we've run the assimilation, we have at our fingertips and we can just use. But they do assume on the calculation of this form. And simply using this, the expected value of the background and analysis residuals gives you an estimation of your observation error correlation matrix. Now, there are a few caveats with these diagnostics. The derivation shows that they're only actually correct when you have the correct observation and background error statistics already in your assimilation, which of course isn't true, because if we already knew them, we wouldn't be estimating them again. But there are some theoretical results that prove what happens from Richard Menard and some work that we've done at Reading that explain what happens when you have errors in your error matrices that you're assimilating. And also, you can iterate this approach to try and get a better estimate of R. But they've been used to estimate error statistics for AIRS, IASI, CRIS, atmospheric motion vectors, radar, Severi. They've been used quite extensively now to estimate these statistics. And I think actually the image that Nancy showed was a de Rosier estimated inter-channel correlation matrix. And they have been taken forward by NWP centers, used and have been beneficial. But what happens when we localize our analysis? Localize our assimilation? So maybe I don't need to explain this to a lot of people here, but local ensemble filters just use a subset of observations given some sort of localization radius delta, which effectively reduces the number of ensemble members that we require. And this is a horrible looking equation, but effectively it's just saying that to update the ensemble mean, we just have a local Kalman gain. So Ki is the local Kalman gain matrix for the ith point in our little example here. And we have a selection operator, phi, which just selects the observations within this radius. Now, I'm not going to go through the derivation of the de Rosier diagnostics in this form, but just to say that we do it element-wise, and we get something that's equal to the element of R plus an element of HBH transpose minus this quantity HF. Anyone wants the details, you're welcome to come and talk to me, but I won't bore you with them. But what it is important to know is when HF, the elements of HF are equal to the elements of HBH transpose. And we don't actually need to do calculation to understand what is in F. We just need to know two things, which is what we call, I do these the opposite way around, the domain of dependence of an observation, which is the set of elements of the model state that are used to calculate the model equivalent of the observation. So take this example. It's exactly the same as on the previous slide, but showing the observations. So say we have Y1, maybe it's just an average of the 4 closest points. Then the domain of dependence will be these 4 points. Similarly, if we take Y4, it would be these 4 model states. So that's one important thing to know. The other thing is the region of influence of an observation. So whereas in this diagram, we're looking at which observations fall within a particular distance of a grid point, we can also consider it kind of the other way around, and we can say, well, which grid points will this observation be used to update? And knowing that information is enough to tell us about the de Rosier diagnostic and when it's useful. So effectively what we need to know is when F is correct and when the elements of the observation operator are 0. So this is related to that domain of dependence, and this is related to the region of influence. And knowing this information, it's possible to determine that the correlation between the errors of observations yi and yj can be estimated using the de Rosier diagnostic only if the domain of dependence for observation yi lies within the region of influence of observation yj. Now, I know that sounds quite complicated, which is why I've got my example running all the way through. So I said, which elements of the observation operator are 0? We can store this in some sort of binary form in a matrix we call C. So again, going back to this one, I'm just using my averaging points. But here, we give C 0 if Hij is 0, or C1 if Hij is non-zero. So I have this matrix. And then which elements of F are incorrect, which is related to this domain of dependence and region of influence. And we can fill this matrix, again, in a binary form, 1s and 0s. And then with a simple multiplication of these, we end up with a resulting matrix. So this is the same size as our R matrix. But here, where we have 0s, it means that we can estimate the error correlations. But where we have numbers, then the estimate from de Rosier's will not be correct. So you might think, well, what on earth is going on? So here, in our example, we're able to estimate our variances correctly. That's because our, all of our domains of dependence lie within our region of influence. And I anticipate for the majority of observation types that this is going to be okay. The only time I can see there being a real issue is maybe if you have a vertical localization and a radiance transfer weighting function that's larger than your localization. Now we can estimate 3, 4, and 4, 3. They might be the wrong way around, because the region of influence covers each other's domain of dependence. But then and we can't estimate these two and these two. But there's a bit of a quirk with this. The way this diagnostic works is that you get this asymmetry. And in this case, you can estimate the correlation between y1 and y2, because the domain of dependence for y1 lies within y2, but not the other way around, because these points fall outside your region of influence. But of course, that's ridiculous, because if you know this value, you know this value. But using the diagnostic, it doesn't allow you to calculate that. So we can say which elements can be calculated and which can't. But does it matter? So now, following that example, so we have still this grid and the 4 observations. We assume that this distance is 1, and everything else is based on that. We can actually choose some values for our R matrix, where we just have a variance times this is the distance between your observations yj and a length scale, and the same for B, where this is the distance between your grid points. And what we can do is we can calculate our de Rosier diagnostic. We're going to do that for a standard ensemble filter and a localized ensemble filter and look at the difference. And what we'll do is we'll consider the percentage relative error between our estimated and the truth relative to the truth. So here I pick my standard deviations as 1 and my length scales as 1. And you might say, well, why have I been talking to you for the last 15 minutes? Because these errors they're about a 10% error. So, I mean, this is a standard de Rosier. You can't expect to do much better than this unless you were increasing your sampling. This is a localized version with the same number of ensemble members as the standard ensemble. I mean, these don't look very different. So maybe it's all okay. Maybe I shouldn't have bothered. But actually, just with a very subtle change of doubling the standard deviation and doubling the length scale parameter in B, you can clearly see now that you're getting these elements, which if I skip back. So it's these bottom 4 that we can get correct, and these 3 that quite clearly, in this case, you can see that you really wouldn't want to be trusting these values. I mean, these are up to 100% error, and that's just with a very slight change in variance and length scale. So I think the message really is if you want to try and use de Rosier with localization, you need to be very cautious about what you can and what you can't estimate. And unless you have some underlying knowledge of the truth, you wouldn't just want to take the values you get because they might be quite considerably wrong. So just to conclude, I think it's clear. Ensemble assimilation schemes are definitely popular. And even and whether that's an ensemble filter or if we're even heading towards particle filters, which we've seen localization applied to this week, yeah, ensemble is definitely looking popular. And what we know about using correlated error in variational schemes at the Met Office and ECMWF, and here at RIKEN there's been some experiments as well, but there is benefit to assimilating correlated observation errors. The more we know about our observations, the better. We have this de Rosier diagnostic that can be used to estimate the observation error statistics. It's cheap, it's easy, and the data is readily available. But they were designed for use with especially in the unbiased estimator schemes and variational schemes. And if we start to localize our problem, then we need to be cautious because the mathematical derivation of this diagnostic no longer holds. And we can show in experiments that we can't recover the R matrix that we're looking for. So I think that's all. Thank you very much.